So what we're going to be talking about today is continuity and discontinuity. So it's what limits have been leading up to, because there's been some of our graphs that look a little funny. And then there's also the case that is a little goofy about limits. This idea that you can have a limit not existing, the relationship between a limit and the f of that function. So when you actually put in that number. So here I've got my function, and right now, f of 3 exists. So here's 1, 2, 3, boom, we've got a point. But we want the limit to not exist. So in this case, the limit does exist. And when we come this way, the graph is heading towards, well, it was about 1. And as we're coming this way, the graph is also heading towards about 1. So we just need to break that idea that it's coming to the same value from both directions. Well, it can be easily done. You could, if you just grab this point and rip it out, that's not changing it. Now the f of 3 still exists. We've got f of 3 up here, but the limit is still heading towards that same value. Sure, they're not matching up, but they are, the limit is still existing. What we need to do is we need to do something like this, where here, as the limit is coming this way, the limit's heading towards 2, and here it's heading towards 1. This is this idea of discontinuity, where the function is not behaving appropriately at certain spots. So here we have a limit, but there's something goofy going on with the function. That's discontinuity. We really like the initial setup where everything was coming together and it was producing a nice result when the limit was matching up with the function. So a function is continuous. You might want to pause. Well, once I say this, function is continuous if the limit is matching up with the value of the function at that point. When it's kind of heading towards something, but at that point it jumps up and does something else, that's not good for our function. That's called discontinuity, which we'll talk about later today. Oh, I think that's the end of that sentence. So if you haven't paused already, go ahead and pause. Now we're back. Oh, now Mel's awake. So here I've got a function, and we're going to look at these various relationships. So I want to know, does f of -1 exist? So does it show up? As we move across this graph, is there a place that I can put in -1? Yeah, I can put it into this bottom thing. So f of -1, it's right there. Yeah, so this totally exists. We can put something in for that. Have a pen, please. Yes. We can also check, does the limit as f of x approaches -1 from the right, does that happen? Yeah, it's heading towards something. So yeah, that works. No problem. Do those two things match up? So is this heading towards the same value that f of 1 is? Well, f of -1 is 0, and the limit as x approaches -1 from the right is also 0, so they do match up. Yes. Since those two things work, f is considered continuous at x equaling -1. So yes. Now this is different than what we were talking about. Does the limit actually exist at this spot? No, because we don't have both directions, but we can say that the function is continuous at that point. So and we're good to go. So we're going to figure out, we want to figure out an alternative formula that is continuous at the indicated point. We did one of these before where we wanted the function to match everywhere except one point. That was the point of discontinuity in the previous example. Now we're just giving another label to something that we've done already. We want to get rid of that denominator because x equaling -3, it's discontinuous there because we've got a hole in the graph, so that's no good. So we want to try to find the alternate version. Well, we'll do it the same way. This is that same direction we got before with just different wording. So I'm going to factor the numerator. We're going to do the kind of factor and cancel method. So we get x plus 3 here. These two pieces cancel out, and we're left with just x minus 3. And we'll give it some function name y, or you could call it g of x. But we're going to say that this is a different function than the original one. As if we still kept it f of x and we're saying, oh, this is just a simplified version of f of x, we'd have to tack on the, well, hey, x can't be -3. We'd still have our hole in our graph. We don't want the hole in the graph. So this is a new function that we're going to say. So this one matches the original f of x, except for that point of discontinuity. So we want to check this thing for discontinuity. It's continuous, except for we've got like trouble in that denominator. So we want to see what's going on in there. So let's factor it. So we get x minus 3, x minus 1. And now neither of those things are canceling out. We talked about a couple times ago, if they're not canceling out, that's when we're going to get the crazy asymptotes. If they had canceled, like that earlier one we did, we would have had just like a little hole, and that would be a removable discontinuity. This one is going to shoot up and down in opposite directions. That is an infinite discontinuity, since they're not canceling. And if you're not sure, you can always just plug it into your graphing calculator and see what's going on, and you can see those cool asymptotes. So these are both infinite and finite discontinuities. I write better in the PDF notes. The second one is nice and continuous. There are no problems going on in this one. If you kind of imagine its graph is the easiest way to talk about it, is it's like x minus 1, so that's just like whoop, whoop. It's just that nice V shape. So there's no points where it's changing where it's headed towards. Here it's heading towards the same thing, heading towards the same thing. In the middle, it's heading towards 0. So everything's working out. We don't have any discontinuities. It's nice and seems to be doing the same thing the whole time. Here's one of those removable discontinuities where it's making that quick jump. So sure, we don't have continuity here. As we're approaching -3 from our right-hand side, we're heading towards 3. As we're coming in from our opposite side, we're also heading towards 3. The limit as f of x approaches c is 3, but this limit is not equaling what f of -3 actually is. F of -3 is 4. Since this is not equal, since those two things are not equal, that is discontinuous. And the type of discontinuity is it is a removable discontinuity. Because if we can just get this thing fixed, just take this point and shove it back down there, then we'd be fine and we'd be able to fix our function. Since it's just one point, we can fix it. Here's another example of that jump discontinuity. So we're coming along this way, and then we suddenly jump up there. So that is our point where it is not continuous. So the point is, it is not, f of x is not continuous at x equaling, what is that, -7? Yep. And is not removable. Now remember, I've mentioned this before, but there's no problem here. So as this function suddenly changes its mind, it's going from linear to quadratic, we don't have any trouble with that function. It is a nice continuous function. So this one is continuous. If you want to see more examples of this type of problem, there are more done in the PDF notes, but I'm running long on time, so 4. Good, and we can see that on our graph. And we want this thing to meet the same spot, so it's A equaling 4. So that is our done thing. Now, what if you want to do that without a graph? So here's an additional example where we do that without our fancy Desmos graphy thing. So we know we have a discontinuity when x minus a equals 0. We know that's going to be trouble. That's where we're getting this kind of like hole in the graph. And we want to figure out, okay, well, where is that problem going to be? So then we can fill that hole with this 8. So we want x to equal 8. Because if we can have x equaling 8, then it will plug in this 8 right there to fill in our hole. So if we can get that A to be filled in with the little piece that we've got, then we're going to be okay. So we can just substitute this in, shove that in there. So 8 minus A equals 0. So we just want A to equal 8. And that'll work. So we won't find the spot that we're having some trouble, figure out where the two are going to meet up. 3. Now, this one is not the one that we were looking for. That one is not between 0 and 5. We were checking for something between 0 and 5. Well, hey, that's 3. 3 is between 0 and 5. So we do have that number between 0 and 5, and it does spit out 11. Now, that seems like a whole big hubbubaloo about nothing. So what's the point of this thing? Well, there's this one, I didn't need the intermediate value theorem. I can figure that out myself. But there's times where it is going to come in handy because there's times we can't really figure it out ourselves, or we don't know for sure that number is there. Check this one out. Any real number exactly 1 less than its 4th power. So I want to know where x is going to equal x minus x to the 4th minus 1. Well, for this, if I wanted to solve this equation, I would say, okay, well, 0 equals, I'll get this thing equal to 0 minus x minus 1. And that's not something I can factor really nicely. But I feel like this should work. This should be a solvable equation. And I can even see that in terms of the graph. But often, so I can tell that there's going to be two numbers, this one and that one. These two numbers are going to work for it, but it seems like I can't solve this equation. Well, the intermediate value theorem is going to tell us that we definitely can solve this equation, that this definitely exists. There's not going to be any funny business going along here where there's suddenly a gap at that spot. I know this is a continuous function. I know the limit is going well on both sides, so I know that point has to exist. Thanks to the intermediate value theorem. Otherwise, we could kind of look at this graph as like, well, yeah, it seems like it's doing that, but how do we know it definitely works? The intermediate value theorem. As a continuous function, it's got different values on both sides, and we should get a nice answer. So these are the two answers that it's looking for. That's the whole point of the intermediate value theorem. And that's it for today. So make sure you check for continuity is when the limit matches and the limit is matching what the function is doing. Point discontinuity is also considered removable discontinuity, so make sure you got those two terms kind of the same. And the intermediate value theorem is the other cool thing that we talked about today. So that's it. Final lesson for the unit. Yay! Have a good day. Bye-bye.